Hello students, today I am going to discuss one of the operating system topic. Deadlock is the main topic, but today the main discussion is all about resource allocation graph, that is RAG. In short, we can denote or represent as RAG, resource allocation graph. This graph is basically used to identify or represent the deadlock in the system. As we know, when deadlock occurs, no process is able to continue further. So, how it can be represented in the system? There are different means by which we can represent deadlock. Resource allocation graph is one of them. Now, this is used to, as already said, this is used to represent the deadlock in the system known as resource allocation graph or RAG. This is a directed graph in nature. That consists of process nodes for a set of processes, active processes P1, P2, P3 up to Pn, and it is represented by circle. And another type of node that is used in this graph is known as resource nodes for a set of resources R1, R2 up to Rm. These are the set of resources available in the system, and this resource node is represented by rectangle. And one thing more, the dot under this rectangle is used to identify the instances of resources. So in this case, if there are two dots, it represents the resource Rj. For resource Rj, two instances are Rj available in the system. Now, the directed graph consists of nodes as well as edges. So, a directed edge from process Pi to resource Rj. Okay. For process Pi to resource Rj, that is P arrow Rj represents that process Pi request for an instance of resource Rj and still waiting for the allocation of that resource. The age in this case is known as request age. Okay. Now, a directed age from resource Rj to process Pi, that is Rj arrow Pi, represents that resource Rj is allocated to a process Pi. In this case, age, the directed age, is known as assignment age. Okay. In this case, the age is known as assignment age. So there are two different types of nodes in this RAG, resource allocation graph, that is process node and resource node, whereas two different types of ages. First is request age and the another one is assignment age. Now, according to definition of resource allocation graph, if a resource allocation graph RAG contains cycle among different nodes, then deadlock exists in the system. And if cycle does not exist, then there is no deadlock. In this resource allocation graph, we also consider the number of instances available of each resource. That is, if each of the resource has exactly one instance, that is quantity is 1, then cycle implies that deadlock has occurred. Means cycle directly represents the deadlock state of the system. So in this case, cycle is both necessary and sufficient condition for existence of deadlock in the graph. Whereas if each of resource has more than one instance, that is quantity is more than 1, then cycle does not necessarily implies that deadlock has occurred. In this case, cycle is in the graph is necessary but not a sufficient condition for occurrence of deadlock. Now, using an example, I am going to construct a resource allocation graph that represents overall state of the system. So in this example, following items are available: a set of processes P1, P2, P3, that is there are 3 processes are available or active at a time, and a set of resources R1, R2, R3 and R4. There are 4 resources where R1 has one instance, means one quantity of R1 is available, whereas for R2 2 instances are available. For resource R3 one instance is available, and for resource R4 3 instances are available. So for 4 different types of resources, the number of instances available are 1, 2, 1, 3 respectively. In this system, the snapshot taken in which the following set of edges are present, that is P1 arrow R1. It implies P1 is requesting for resource R1. So in this graph, we connect an edge from P1 to R1. Next edge is P2 to R3. That is P2 also wants an instance of resource R3. Next, R1 arrow P2, that is this instance of R1 is allocated to process P2. Next is R2 arrow P2. It means one instance of R2 is allocated to process P2. Next is R2 arrow P1, that is one instance of R2 is allocated to process P1, and R3 arrow P3, that is one instance of R3 is allocated to P3. So with the help of the snapshot taken, the state or status of edges in the system is as follows, and using this we connect process to resource and resource to process edge. This edge is known as request edge, and this edge is known as assignment edge, as it is already discussed. When a resource is allocated to requesting process, then this request is converted into assignment edge immediately. So at the particular time, this is the state of the system in which P1 requesting for R1, P2 have one resource, one instance of R1 and one instance of R2, whereas P3 has one instance of R3 and P1 has one instance of R2, whereas P1 requesting for R1, P2 requesting for R3. This is the state of the system. Now suppose at time t1, next time slot, process P3 request for an instance of R2, that is one edge P3 arrow R2 is added in the system. This is the new edge, and for this one request edge is added to the system or resource allocation graph from process P3 to resource R2. By connecting this edge or adding this edge, formation of cycle is shown, which is not present in the earlier case. So, in this addition, before this addition, suppose once again we remove this edge, and at time t0 there is no cycle in the system because the directed edge is used to form a cycle in this graph. But when we connect new edge from P3 to R2, then two cycles are seen in this graph. Let us see the cycle. The cycles are: first, from P1 arrow R1, P1 arrow R1, arrow P2, arrow R3, arrow P3, arrow R2, arrow P1. So, by this addition of an edge, one cycle is this, in which we start from P1 and we end to P1 also. And the second cycle is from P2 R3, from R3 P3, from P3 R2, and from R2 again P2. So this also formed a cycle. So by using this additional edge, which is added due to new demand of process P3 for resource R2, two cycles are formed in this case. So when cycle form in the resource allocation graph, then this represents the deadlock state of the system. Now, I am considering an example by which we can see that if each resource type has several instances, then a cycle does not necessarily imply that a deadlock has occurred. In this case, a cycle in the graph is necessary but not a sufficient condition for the existence of deadlock. So in this example, I am considering a set of processes P1, P2, P3 and P4, whereas a set of resources R1 and R2. With R1 have 2 instances and R2 has 2 instances. And a set of edges P1 arrow R1, that is P1 is requesting for an instance of R1. So I connect this edge from this R1 arrow P2, that is one instance of R1 is allocated to P2. R1 arrow P3, that is one instance of R1 is allocated to P3. P3 arrow R2, that is P3 wants an instance of R2. R2 arrow P1, that is one instance of R2 is allocated to P1, and R2 arrow P4, that is one instance of R2 is allocated to P4. Now, in this graph, resource allocation graph, there exists one cycle, as we see here. That cycle is P1, R1, P3, P3, R2 and again P1. So there is one cycle in this graph, but these processes are not in deadlock because when P4, which is allocated one instance of R2, completed their task, then it releases the instance of R2, and after that this instance of R2 can be allocated to P3. So by this assignment request is cancelled, will be cancelled, and an assignment is from R2 to P3 will be added to the system or graph. So this breaks the cycle exists. So by this example we see that the cycle is not a sufficient condition for existence of deadlock. This is all about resource allocation graph.